Welcome back, everybody. So today we'll be first talking about the flow through the packed bed, dynamics of the absorption column, and PSA, TSA, and VSA. Okay, so we'll see what are these, right? So first is that one of the big thing is that when you try to design a absorption column or any bed, there are a couple of things that you really need to consider. One is the surface area. So when you look into a particular adsorbent, the adsorbent itself has got or provide you the surface area that you need for the adsorption to take place. However, one of the important thing there is that when the gas flows through it, does the gas has the access to the surface area? So I think that is one of the biggest thing in the design of the contactor that which we really need to have, because without the surface area available there, the adsorption cannot effectively take place. So these are the different beds that actually gives you different type of surface area. We are mainly be focusing on to the packed bed. So I have a plan that on the final day, like on the 5th or the Friday's class, we'll be discussing some of other type of the bed that do exist. So packed bed is not only the only type of the bed that do exist. And today and tomorrow we'll be discussing some of the positive aspects of the packed bed, some of the problems with the packed bed, and that way it will help you for your design. But the other type of bed that remains there is the moving bed, like the entire bed itself actually moves, and that actually in a packed bed, remember one of the things that which we always say is an issue is the solid cannot leave anywhere. So if the solid cannot leave, nobody can take away the heat, right? With moving bed, the solids flow out of the systems and it can help you. Then also bubbling bed and circulating fluidized bed, their hydrodynamics are different. So those hydrodynamics that Dr. Pala will be discussing today and we'll be modeling that tomorrow. These are all for the packed bed. These moving, bubbling, circulating beds has got a completely different type of hydrodynamics. When you design this, and again, we will be talking about the design equations, and I know we are just discussing with Dr. Pala here that what he is going to cover today and also early tomorrow is that he will be discussing a lot of these design equations. So when you look into the equations he presents there, you need to keep in mind that what it actually caters to. First is mass transfer. So when you actually design a bed, the big issue is that which mechanism is limiting. So quite often you can come up with an adsorbent, might have a very wonderful properties in terms of the isotherm and everything. But when you look at the performance of that adsorbent in a bed, you may only be realizing 10 to 20% of it. So actually, it might not even make sense to go for a great equilibrium and all those kind of things because you may not even realize it. So it's just sitting there, and basically a large portion of the bed may not do anything at all. This is the issue, like as you have done with the plug flow reactor. As you know that we always complain that you have a catalyst which contains costly material like platinum, and you must utilize it, right? Because otherwise you provide platinum, it doesn't do anything. This same issue can happen here. So you have to find out what is the rate limiting mechanism and how do you actually minimize that rate limiting mechanism. The other thing is that these are a lot of these conditions, that what is the inlet concentration and the desired outlet concentration of key species. So I will be discussing some of these from the perspective of your backend, which I discussed also in the first day, that when you design a CO2 capture system, it's not only the upfront, it's not only the capture, but you have to keep in mind what you are doing with the CO2 that you are desorbing. That's very important actually. So we'll be talking about that. The other design criteria that you need to consider is the extent of capture, that how much you want to capture here. Then you need to consider what is your driving force here. The other problem is the heat transfer. So in today's class, we'll be discussing quite a bit in terms of the heat transfer for these beds actually. And that is in the bare bone model that you will have in Aspen AdSave. Lot of these things will not actually, it will not give you access to doing a lot of these things. So question is, how do I embed all of those things? That's a design criteria that we really need to keep in mind. So I know at this part of the workshop, what we are trying to will be trying to do is that, well, I can build a model in Aspen AdSim. If we can do that at the end of the day, like by the end of Friday, we are in a great shape. But when you go home and start working on the problem, the first thing that you do is that, well, now I can build a model in AdSim, but so what? What do I do with that, right? Then you really need to think about these design criteria because they give you the performance of the overall system. So we'll be talking more about that. Then the other thing is adsorbent particle size is a very important thing. So what should be the particle size? So when we do it in the lab scale, it's often in form of a powder, right? Now when you take it to a fixed bed and do it in real life, you cannot get it in form of a powder in a pressure swing adsorption or anything. This entire material will be taken off by the gas. It will be taken or carried away with the gas. So you have to have a particle size that will make it stay inside the bed, right? So you have to, then the question is, when you start from the powder to a particle, you might actually land up with a lot of resistances in terms of the mass transfer resistances and heat transfer resistances. So it's not arbitrary. So that is where the people who develop the commercial catalyst, their expertise lies, that how to take the lab scale powder and move it to a real life operations, but without creating the resistances, mass transfer resistances. So that's a design criteria that you have to keep in mind. When you do it in Aspen, sometimes it's misleading. We are looking for a parameter. We are saying, oh, keep the void is like 0.4. But you have to understand that in really, you have to realize that when you put it in the real life, whether you will get a value of 0.3 or you will get a 0.6 or you will get a Knudsen diffusions or you will find out like there is mass transfer resistances that 90% of the particle is not accessible to the gas. That depends on the structure of the particle, and that is something that we have to keep in mind. The other thing is that if you are using bubbling bed or fluidized bed, you have to think about the fluidizability of the particle, right? When you have this particle, if you say this, my particles, when they heat with each other, they will break apart, then that type of particle is not good to be used in a fluidized bed. Because in a fluidized bed, the particle will collide with each other and they can break only to some extent, but they should not be like breaking into small pieces because then you cannot have them inside the bed. It will be carried with the gas from the bed. So the particle attrition resistance is an important thing when you try to do this. But now, if you have a particle that is, yeah, it's not very good attrition resistance, then you can use them in moving bed. So the moving bed is a good compromise between fixed bed and the fluidized bed, right? Because they have got, these are much packed bed and it will, the entire bed will move through the system. They do not collide with each other so much like a fluidized bed. So all of those things are important things to consider. Okay, so these are general process design conditions. So anybody has any query for this part?
In that situation, see that the absorbent particle, that's really very important basically when
Right.
carefully only design the particle size. Otherwise, what will happen? Normally, you see any boiler systems, one ID panel with the P panel with the inside element, the pressure is very important.
Yes.
Because of the differential
Yes. Yes.
suppose particles is very minute size inside, it will carry away along
Yes.
with the gases. So
Absolutely.
I think,
Yeah.
you have to retain that the particles
Particle inside the bed.
but the maintain best to protect and
Yeah.
interact with the gas.
Yeah.
So that the entire surface of that particle will be have contact with the gas to capture the fluid.
Absolutely.
Something difficult is there in the real world.
Right, and that is where like a lot of people have come with different type of a structure. Like one of the commercial designers that which we work with, they had the same particle, they put it in a honeycomb type of a structure. So those type of structures give you a very low pressure drop, but it will give you really good exposure to the surface area. And they got this idea from the SCR process, or selective catalytic reduction process, that is used for NOx reduction. If you go to a power plant, you will see SCR everywhere pretty much. So that technology, they got it here and then they do it here. Another one wanted to put it in from a pellets actually. So it's basically almost like look like a blade of a fan. So you put it like this, all these channels, and this will actually flow through that pathways. So you have to be very careful about how you design it. We will not be discussing or be talking about a lot of those things as part of this class, but what I wanted to tell you that our yesterday's lecture was really meant to say that if you know Aspen Custom Modeler, you can do pretty much anything and everything with Aspen AdSim, because it gives you the whole flexibility of writing your own equation, writing your own design criteria and everything. Right. Yeah. Okay. So this one is the standard bed, and you have already seen this. The couple of things that you have to remember in here is that for this pack bed, this adsorption capacity is finite, which you think will make sense, right? Because we have a maximum loading, right? So we say what is the maximum loading that we'll have here. Now, this is also, I keep saying this, that this is an unsteady state operation, right? So what would happen is this, the concentration of the adsorbate will goes up with time. So this will actually load first, then go here, then go here, then go here. And the reason it happened there, and I know that yesterday Dr. Datta was discussed about the breakthrough curve and all of those things there. But the point you have to realize inside your mind here is that the reason that this portion gets loaded first is that they see high partial pressure of CO2. So when the gas leaves from this section, is very low partial pressure of CO2. So these guys has got really nothing to absorb. So once these guys get saturated or gets close to the equilibrium, then they cannot capture anymore. Then the gas over here will have higher CO2 concentration, and then they will take their turn, and they will take their turn, and they will take their turn. These guys at the end may never take their turn. It really depends upon their mass transfer resistances and other kinetics. So a portion of the bed may really do nothing and it has already broken through there. And that's really the thing that you have to think about it. So the question that comes there is, from a design perspective, instead of arranging it this way, would I have arranged it in some other way? Right? This is, and we do not talk, we do not discuss this, but this is known as this typical picture that we are showing. This is axial flow fixed bed. But a counter to this is there is also a radial flow fixed bed. So in the radial flow fixed bed, the same thing is there, but we rotate it sideways, okay? This portion is sealed. So this could be the gas. Gas in, and this is the gas out. This is gas out. So there is an internal channel, and instead of this passing through this in a radial flow bed, this is a radial flow bed, it goes here and then moves on the sidewise. So what is the advantage or disadvantage here? Just from the shape of it, can anybody imagine what is the pluses and minuses with this type of bed? What is the key differences between that orientation and this orientation? Sorry? Right, and because of, correct, correct. The main thing what you have to realize here is, what is the cross-sectional area for this bed? What is the cross-sectional area? Pi r square, right? And that's constant because the bed is constant. So cross-sectional area does not change. Here, it's changing. It keeps changing actually because R is changing, right? So what happens is that when you come here, you have got a very high cross-sectional area. Here, very low. So this will actually speed up, but here it will actually slow down quite a bit. So if you say, I want a very high residence time over here, this type of bed can actually give you, really help you, because you can design this bed in such a way that it flows through one direction during adsorption, during desorption it flows through the other direction. This type of bed actually leads to very, very low pressure drop compared to that type of bed. And I will show you, if time permits, the differences in the results. So very low delta P, right? So as Dr. Sathuraman was saying, that we have to keep in mind that there is a blower as part of, like if I'm doing a power plant capture, we have a blower there, and that how much pressure drop is needed for flowing through these ones. So this type of bed are actually very nice for that one. Pressure drop is almost zero actually, negligible because of this compared to the same type of. So this is a criteria that you have to keep in mind. So you can be imaginative in terms of all kind of bed design which many developers are doing. So developing an adsorbent is only one piece of the puzzle, but then there are many others. So that's the point we wanted to mention. Yes, please. Right, 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 right. This is also, as you were also mentioning, that in terms of the height, you can actually take place and you can make it wider instead of making it a very tall tower there. And once you have it very tall, and you will see the pressure drop is also very high. So here it gives you the advantages of doing it this way. But these things do not come without a challenge. One of the challenge that, again, we know is actually the channeling problem. So So basically, when it goes through here, the pressure, even though it's a channel, it is expected to go down. So it might so happen that most of the gas tries to pass through this one, and you will may have a non-uniform distribution. So you have to be innovative in terms of your design, that how to ensure that it has a uniform distribution. Yeah, please.
We can have a heat transfer, like heat exchanger kind of arrangement, putting backwards and all to increase the residence time.
There are actually for these ones, people do actually all kind of design to ensure that there is that you can reduce the channeling. So it has been commercially done. Even like you could have shroud the half of the bed if you are operating at a lower flow rate and all of these things. So you can make it actually half bed actually. So it will, you can block it like this top corner can be actually put up and down based on your flow rate. That design also exists. And also just like what you said, for the heat exchangers, you ensure that it is actually not channeling there. But yes, so all of these are gives you a lot of design criteria. So I wanted to say that other side you must consider once you develop the model is the design of this type of beds. Sorry? Yeah, so for these type of cases, basically the idea there is that, remember what we are trying to do here is they can be co-current or counter-current. So when you do the desorption, so if we are doing adsorption this way, the desorption can come this way, or if I'm doing adsorption this way, the desorption gas can be this way, or both can be at the same direction. So it could be both, it can be co-current or the counter-current. And that's an optimization problem that you have to solve to find out what should be the configuration. That depends upon your gas composition. So if you have a high concentration of CO2 or low concentration of CO2, it all depends on that. If you have a low concentration CO2, you want actually very high residence time for that guy to capture it. So you will push it from this side actually, so that it has got a very high residence time when the partial pressure is high. So this portion of the bed will actually capture more. Here it will speed up, but you also have less amount of material there, so you don't worry about it. So it does not capture much, but much material. Yes, I'm shrinking. Yeah, it has to be measured given your flue gas or the gas concentration of CO2. Okay. Go ahead.
Absorption material. It looks like a small cylindrical parts, spherical parts, sponsors. So when the gas is CO2 is absorbed in that spherical parts, suppose you want to remove that CO2, then naturally you can take it out of the parts and again do some kind of work for the CO2 can be removed. In this case, since it is fixed cylindrical type, what get absorbed inside the material. So I think it's a problem is going to remove that CO2 from the space. That's easy. But how we can remove this captured CO2 from this kind of cylindrical fixed one?
If you really want to move or take out the solid from the bed for regeneration, we should not go for a fixed bed, because then you will have to go for moving bed, bubbling bed, circulating fluid bed. But because of this packed bed also, you cannot take it out, irrespective of axial flow and all of this, because the hydrodynamics will not permit you to do that. If you have to move the solid, you have to go to the different flow regime actually. So that's the issue there. So irrespective of whichever bed we consider, we cannot do that.
Take out the captured CO2 from this
You'll have to heat it up. So we'll talk about that. It's the regeneration you have to do, and we'll talk about that. That's a cycle setup actually. Yeah, absolutely. That's a cycle setup. But if you have to take it out, I will go for one of this type of bed. You had a question?
We have cryogenic air separation units wherein we are separating CO2 and moisture
Right,
using these dryers.
Right.
So there we have two dryers. One
Yeah.
will be in line, the other will be in region.
Absolutely.
So my doubt is we have packet beds only. So we'll be sending the air. So inside the bed, will that be in a fluidized state then?
No. The cryogenic systems that which you are actually considering, those are all packed bed and fixed packed bed. And the reason why we still work with the fixed packed bed in cryogenic separation, because you are separating CO2 from air. Whereas air CO2 is only in the ppm level. So you can afford to have the bed sitting there for a long time and then you take it out and you do it. But the problem with these type of systems, like if you look into the power plant, as I was saying, this is like an ocean of gas that is flowing through. So it's a 35 or 36 billion ton of CO2 we are talking about. So that is where these thoughts have to come into picture, that is fixed bed sufficient. So I will show you some of the numbers. It can be actually ridiculously high. I will show you some numbers from our studies. Like in some cases, you might need actually 100 fixed bed operating in parallel. So the gas comes and you have to distribute it into 100 beds actually for a single power plant. So that is where this type of bed is very helpful. Yeah, it's because of the quantity of the CO2. Okay, any other? Yeah. Yeah, so if you look into the hydrodynamics of the moving bed, so this actually goes like this. So this whole thing actually moves, as opposed to if I'm looking into bubbling fluidized bed, these are much separated. So the gas is there, and because the gas is there, this guy will go and hit with each other. They collide with each other. So gas actually gets that and throws it there. But this is actually more compact bed and flows through the system. So that's how resistance is much less. Okay, unless there is any other questions, we'll move here. Okay, the what you have to really need that when the bed must be taken offline, okay, when you have that overall loading goes high. So during that time, you need additional bed, right? So, and we'll be discussing more about that. Like this is a very tricky problem to discuss there. How many additional bed do I need there? So basically what happens is that adsorption, desorption continue with some additional steps in between. So, and we'll talk about that, what additional steps may or may not be needed for any of these systems. So in general, how it actually looks like. So what you will be finding here is that if you are looking into, this is how it is coming in here, okay? And then this is kind of a saturated zone. This is a little bit saturated, and then it is goes there. And then what happens is the concentration actually, notice that if it has already saturated, it is something happening with time. So this is at a given time. So think about a time when this portion has mostly got saturated. Around that time, you notice that the concentration around this section does not really drop. It's a horizontal line because this portion of the bed is not really capturing much. This portion is taking its turn around that time. So if you notice here that this portion, the concentration is going down, and this portion is really doing nothing. So this portion is idling because the concentration is so low that it has really nothing to capture. After some time, this front will keep moving. So this saturated portion will expand here, and this portion will expand here, and this fresh portion will keep shrinking. What we want ideally, if you can, the entire portion of the bed becomes saturated. So this whole thing should be moved here at time. That is where the overall system and the kinetics become so important, because quite often this is almost the best that you can get. By the time it had already broken through and you basically say, sorry, I have to take the bed off. And that is one of the biggest issues while designing this type of bed. So if you look into it, basically it's the same thing, but showing it in a little bit different way. This is showing it with respect to the time, right? So that was with respect to space. Now it is showing it with respect to time. So what it is actually showing you here is that when you look into that outlet gas flow at this time, it is only the top portion of the bed is saturated. Then this portion is actually undergoing adsorption and this portion is clean. As the time progresses, like here, this guy is taking its turn and this portion is now undergoing adsorption. This is clean, and with time, this portion is then taking its turn. What you look into at the breakthrough curve is this guy. So what is the problem that we have here is that we do not see what is happening inside the bed. If you're just observing at the outlet, you do not. Oh, okay, sorry. Okay, so if you're looking into the curve here and looking at the outlet concentration, like this guy at the outlet concentration, you see really nothing is happening. So it is T1 here, but inside the bed, the front is actually moving, right? These things is known as the moving front problem. So if you are observing or measuring this at the lab scale and you do a breakthrough curve, this can be pretty confusing because you have no idea what is happening. Suddenly it shows up, but at that point does not give you a very clear indication of what has happened in the bed. That is why we really need to do the simulation, because that will tell you that how much of the bed is actually getting utilized here. So this is basically how it actually looks like. So this is the breakthrough curve here, but just we always define the breakthrough curve for the outlet. But actually the breakthrough happens at every location. So breakthrough means something is breaking through. So this point will have broken through very early. This point has broken through at a later point, and this is the point when it has broken through. Then only I can see it because I'm only measuring the concentration over here. So this thought is actually very important to carry in your mind as you do develop your models and the simulation. And when we'll talk about the performance curve and performance measure tomorrow, you will see that we'll be discussing these things more in details. Okay, any questions here so far? Okay. So there is something called an adsorption zone. This length of the adsorption zone, wherever this adsorption is taking place at any point of time, so up to which it is getting saturated, this is the function of the rate of transfer from absorbent from the gas to the adsorbent, and that is where our mathematical model tell you or let you figure out how it is going. If you have a shallow adsorbent zone, that indicates that it's almost like saying that we have gotten a good utilizations and they will be giving you a step-like breakthrough curve. So if you're looking into this, you really do not want this S-type breakthrough curve. What you really want is a breakthrough curve the ideal breakthrough curve is this. This is, you can say, an ideal breakthrough curve. In reality, what happens is that it will start curving from here. Something like that. So this is the reality. Or it will be like this. So closer and closer you can bring it to this place, better off you are. Okay. As I said, that only you will see 30 to 40% of the bed is actually utilized, and that is where the problem is there. Of course, the lower mass transfer resistance will lead to longer breakthrough time for the same bed size and vice versa. This is actually one, I will show you results from two of our papers. Yeah, go ahead.
Sir, this breakthrough curve is probably assuming we have a Langmuir kind of isotherm and adsorption gets saturated. But it is like, if it is like PET isotherm or any other isotherm which has multiple peaks and all, will that be so simple?
It will not be. This breakthrough curve has got two assumptions here. One is in terms of the mass transfer resistance, how you are modeling that, and what type of an isotherm. It's a result of both of them. But depending on the type of an isotherm, there could be multiple breakthroughs. So there could be even cases like these and like these, and yes, all kind of breakthroughs are possible. Absolutely. Yeah, that's a good comment. Yeah, it all depends upon isotherm model, kinetics, and what is the dominating impact that you have. So this is something I thought I will bring from one of our papers there, and which kind of shows you that how the breakthrough takes place. So look into here, like this is one of the papers we did. It's a fixed bed reactor, but it's a micro encapsulated solvent. Again, you can think about this as a sorbent, but this is basically like if I take you a balloon and put water into it, but instead of water, you put a solvent inside it. Okay, small particle like 50 micron balloon, and then within that 50 micron balloon, I put liquid in it. And that is this guy actually, this microencapsulated solvent. This is not our technology because we are modeling people. This was done by Dr. Josh Stolaroff from Lawrence Livermore National Lab. So it's and Catherine Hornbostel there. Those are the technology developers for these ones. But nevertheless, this shows you that how the breakthrough looks like. So look into that. There are two things we are showing here. So first thing is that you see that this is showing it with respect to time. Now, if you are looking into the breakthrough here, right? So you notice that towards the entrance, so one is the entrance, you get the breakthrough at any given time right away. Then another time you are seeing this, and this is a front that is actually progressing. And then what you see, the loading of it, the loading actually does the same way. So the front portion does not load at all. The later portion start loading here, and that other portion actually start loading afterwards. Okay. So this is one interesting thing that what you actually can find out, that with respect to the bed. The one thing not to confuse this, that this time is actually residence time. So think of this as about the length of the system. Okay, so not to be confused with the breakthrough time or actual time. This is the residence time. So this is actually the length of the system. So up to this is like the length, the entire length of the bed actually. So, but this gives you a very good idea how this font actually keeps propagating. So keep in mind here that if I'm at 75 seconds, for example, it already broke through from the beginning of it. Kind of, right? And at 100, you see there is really not much of a difference, because actually this guy is not doing anything at this point. Now, when you go to the middle of it, you will see already it started showing up over here. At that time, there is really nothing happening over here at 75 seconds. And then at the 100th second time, you will see that actually it started showing up. But all of them are going to the same value. But if I would consider the breakthrough here, it has already breakthrough just in the beginning. This tells you that how the bed should be sized, because if my bed size would have been for the residence time here and my breakthrough was somewhere here, I have almost instantaneously broken through, right? So this gives you that what should be the bed length. So this is how you actually can simulate a very long bed, and then looking into it, then you can actually say chop it and say, okay, this is where the my bed size should be. So you can do always a longer bed, and then after you simulate these breakthrough curves, that will actually help you to design the bed there. So that part, and the corresponding thing here is actually the loading, and you see that front portion, it actually does not, the loading does not change very much after some time, but in the second and the third portion actually then take their turn and their loading actually keeps going. But the interesting thing to note that is the front portion actually goes to the maximum loading here, but these portions only after such a residence time will give you that same amount of loading. So if I would have my bed length like this, like if the bed length was equivalent to this portion has so much of the loading, this portion will have like a half of the loading, and this portion really doesn't capture anything. And this is the issue that which I was talking about, that you have to really think about that part. Another result I'll show you is that this is for, this has got a temperature. That's what I wanted to show you here. This is for so the one that we had over here, this is a solvent. And you might argue, why you are using a solvent here, putting it within a balloon rather than using a distillation tower, right? That's a natural question. This is actually a solvent that we are using. These are actually highly viscous solvent. So it is so viscous that it will actually doesn't want to flow through the distillation tower, or you have to basically heat up quite a bit and all of those. But this has got a very high capacity there. And if any of you are aware of it, like if any of you are from natural gas sweetening processes, or you know these those processes, there is this hot caustic wash processes people have used for sulfur removal, right? Potassium hydroxide and sodium hydroxide people have used there in natural gas sweetening processes. You have to heat it up to quite a bit temperature to actually make those guys flow, those solvents to flow. Otherwise, it is very viscous. So if you have a viscous solvent, this is the way to utilize this. Like I'm not a technology developer, so I do not know this. This is specialized equipment that these guys actually develop, that in a 50 micron, this guy comes and put the thing and put it in the balloon, put it like, it's like a drop of solvent and put it inside the balloon. So it's a complicated manufacturing technology, but that is why we did that actually. It's a solvent. This guy is a metal organic framework. This is my student Ryan Hughes actually worked on that one, and this is a diamine appended metal organic framework here, and Professor Jeff Long from University of California, Berkeley, actually is one of the lead developer as part of this work. Actually, Rebecca and other guys from their group also was actively working with us on this one. So this is even more interesting. This has got a very high heat of adsorption. So see what happens when you have a high heat of adsorption. So this has got about 65 kilojoule per mole heat of adsorption. So if you look into the loading, even with respect to time, you see at the entrance, it goes up, and then first it goes up very quickly, and then it slowly goes up. The second portion, now the middle of it, now takes its turn, and then at the end, the exit takes its turn. But this is the maximum loading that you could have gotten for this metal organic framework. but in reality, you are getting the more than 50% of the bed is only getting 2.5 over 5, like only 20% loading than what you could get from equilibrium. And the reason is because the temperature is going up. So the moment it captures, this is the issue with the fixed bed, because when capturing it, the heat is released and it will immediately shoot up. Immediately when it shoots up, it will affect your isotherm. So again, when Dr. Pala actually discusses all of those today, and I know yesterday you had some discussion about the isotherm, you will see that it does not favor your equilibrium. So higher temperature hurts you in terms of loading. So temperature goes up. That's why you never can capture this. So you notice that they go to the same loading because they go to the same temperature. Now, looking at this curve, can any of you guess why this shoots up and then slowly starts increasing? So it's almost like a step-like thing, and then it slowly goes up. Exactly. The temperature, you see the temperature drops, and then temperature increases first, and then the temperature drops. So this temperature drop corresponds to this increase. So why does this temperature drop? Right. So your heat, exactly, the heat that is taken away from the convection is more than the heat generated due to the adsorption. So you see that this how each other, right? So at this point, the heat generated through adsorption is much more than the convection. So the temperature shoots up. But later on, it's the convection which is dominant, and that's why the temperature drops. As the temperature drops, this favors these ones. This is also done using AdSim. However, this isotherm. Correct.
Does it mean that in the middle there is no convection?
No, there is convection. So this is a great question, and anybody wants to take a shot at it. And I was trying to get into that one, but yes. Exactly. That is what is happening. So this temperature that from the front portion, that is cooling, but because it is cooling, the later portion is already getting the flue gas which is already hot, so they cannot cool down. So when this is coming, the gas is coming at 25 degree or so. Okay, that's why this front portion cools, but because the front portion cools, the gas already gets heated up. So when it reaches the middle portion, it is already hot, so it cannot cool it down. It's very interesting if you really think about how this happens, but the mathematical model will actually show you all these complicated interactions that is taking place. Okay.